All right, today we're diving into an element that has, well, a bit of a split personality. It's a metal that not only built the industrial world of the past, but is now kind of quietly powering our future. This is the story of vanadium, the element of two faces.
So let me ask you a question. What on earth could possibly connect the car that started it all, a modern skyscraper that can withstand earthquakes, and the biggest challenge we face with our energy grid? I mean, they seem completely unrelated, right? But they all share one single secret ingredient.
And the answer, believe it or not, is vanadium. Yep, element number 23 on the periodic table. It's one of those metals you've probably heard of, but whose real story is so much more dramatic and, frankly, more important than you could possibly imagine.
Vanadium's story doesn't start with a bang. It actually starts with a bit of a scientific tragedy. It's this bizarre case of mistaken identity that's set back its progress for decades. This is the story of how an element was discovered not once, but twice. So get this, way back in 1801, a mineralogist in Mexico named Andrés Manuel del Rio was sure he'd found a new element. But just 4 years later, a very prominent French chemist basically dismissed his work saying, nah, that's just some dirty chromium. And Del Rio, lacking the clout to really push back against the establishment, actually retracted his own discovery. It's wild. The element was just lost to science for almost 30 years, until it was rediscovered in Sweden and finally given the name we know today, vanadium.
So let's get into the first phase of vanadium. This is the one that really lit a fire under the Second Industrial Revolution and, built the modern world as we know it. Let's talk about vanadium, the strengthener.
The big breakthrough moment. You're not going to believe where it came from. A car crash. Seriously. In 1905, Henry Ford was looking over the wreck of this high-end French race car, and he noticed something weird. The parts were way lighter, but also much stronger than anything he'd ever seen. He had stumbled upon a metallurgical secret. It was steel mixed with a little bit of vanadium.
And here is the absolutely mind-blowing part. The amount he found was tiny. Ford figured out that adding just 0.2% vanadium to steel literally doubled its strength and made it 30% lighter. This wasn't just a small improvement, this was the golden ticket. It was the key that unlocked mass production and made the iconic Ford Model T a reality for everyone.
So how in the world does that work? Well, the science behind it is called precipitation strengthening. When you mix that tiny bit of vanadium into hot steel, it forms these incredibly small, super hard particles. The best way to think about it is like microscopic rebar, reinforcing the steel from the inside out. It stops the steel's internal structure from shifting around under stress. And that's where all that incredible strength comes from.
And this wasn't just some one-hit wonder for the Model T. Nope. Today, this exact same principle is everywhere. It's in the rebar that makes our skyscrapers able to withstand earthquakes. It makes our cars and jet engines lighter and more fuel efficient. It's used to make the super hard tool steel that cuts and shapes pretty much all other metals, and even the rails that our fastest trains ride on.
Okay, so that's phase number one. Pretty impressive, right? But believe it or not, that's only half the story. Now we need to pivot and look at the second phase of vanadium, a much more modern identity that might be even more crucial for our future. Let's talk about vanadium, the energy storer.
We all know the biggest hurdle with renewable energy, right? The sun doesn't always shine, the wind doesn't always blow. It's fantastic when it works, but it's intermittent. So, if we're ever going to truly switch to a green grid, we desperately need a way to store massive amounts of energy for when we need it. And this is where vanadium's other personality comes into play.
So, meet the vanadium redox flow battery, a VRFB for short. Now, unlike a regular battery that stores its juice in solid parts, a flow battery stores energy in a liquid. It's a brilliantly simple idea, really. You have two big tanks of a vanadium-based liquid, an electrolyte, and you pump these liquids past each other with just a thin membrane in between. The exchange of ions across that little membrane is what stores and releases electricity.
So, how does this stack up against the lithium-ion batteries we all have in our phones and cars? Well, it's not even close. A vanadium battery can be charged and discharged over 15,000 times. That's at least 5 times more than lithium-ion. And because the electrolyte is mostly water, it doesn't catch fire. The risk is basically zero. Its capacity never fades over time. But here's the real kicker, scalability. To get more energy storage, you don't need to build a whole new, bigger battery. You just need a bigger tank of liquid. That's it. And when we say a bigger tank, we are not kidding. This right here is what grid-scale energy storage actually looks like. Each one of these massive containers holds that vanadium electrolyte, and altogether they form a single battery, powerful enough to stabilize an entire region's power supply. And if you want proof that this isn't just some lab experiment, look no further. The world's largest vanadium flow battery in Dalian, China, is an absolute game changer. It can store enough energy to power 200,000 homes. It works like a giant energy sponge, soaking up all that extra solar and wind power when it's available, and then just releasing it back into the grid during peak hours to stop blackouts. This is real, and it's happening right now.
So there you have it. We've got the two faces, the strengthener that built our past and the energy storer that's building our future. And this dual importance, this incredible versatility, has made vanadium a truly critical metal for the modern world.
But there's a catch, and this is where things get really complicated. Just look at this. For a country like the United States, it has to import 94% of its vanadium. 94%. And a huge chunk of that comes from Russia and China. This kind of dependency on a metal that is so vital for both our basic infrastructure and our energy security is exactly why it's been officially labeled a critical mineral.
And here's where the two faces of vanadium really come full circle in a surprising way. That first job it had as a strengthener is having a massive green impact right now. By making steel lighter, vanadium alloys save something like 185 million metric tons of CO2 every single year. To put that in perspective, that's like taking 40 million cars off the road permanently.
So here's the bottom line. Vanadium really does hold the keys to a stronger, more resilient, and greener world. It's this incredible element that can reinforce our buildings and recharge our cities. But this leaves us with a really tough final question. Can we actually build that future on a metal that, for many of us, we don't control? It's a challenge that ties together metallurgy, energy, and geopolitics. And how we answer it is going to shape the century to come.